And so fractions, decimals, and other numbers. So there was a question on activity number 9 that asked if you have a fraction like 1/2, 1/4, 1/5, how can you tell by looking at the denominator how many places are going to happen before it terminates? So 1/2 is 0.5, 1/4 is 0.25, 1/5, anybody? 0.2. 0.2. Anybody know 1/8?
0.125.
Nice, 0.125. So I'm picking numbers that happen to terminate 1/20th.
You don't know that one? What's the same as?
Let's see.
0.05.
0.05, there you go. Okay. So is there a way to look at the denominator and say, oh, I know it's going to take 1 place, or 2 places, or 3 places? What could we do to analyze the denominators?
Factor.
We could factor them. Yeah. So 2 doesn't really factor. I mean, 2 I could say is 2 to the first power. Oh, that's interesting. 2 to the first power at 1 place. 4 factored is what? That's prime, so it would be 2 squared, right? 5 factored?
2, 5 squared.
5 reversed. 8? 8 to the cube. Try what?
2 cubed.
2 cubed, yeah, 2 cubed. 8 is 2 cubed. What's 20?
5 to the 4th.
Nope.
No.
That's a good guess.
5 to the 2nd.
No. Come on, do a
10 to the
factor
2nd.
tree. Oh my gosh, you guys are killing me here. We're regressing.
Squared.
What is it?
5 and 2 squared.
Nope. Oh yeah, yeah, right. It's 5 and, oh wait, is it?
5.
Yeah, 5 and 2 squared. Yeah, it's 5 to the first times 2 to the second.
Oh,
Is that Debbie out there?
so 5
Yes.
to the first
I
times
think she was yelling.
2 to the
Oh,
2nd.
am I muting her or something? No, she's not muted. Can you hear me?
Yeah, I can hear you.
Oh, good. We were off playing in the computer lab. We just got back.
Okay, that would explain it.
All right, so Debbie, this relates to a question you asked on the homework. This is question number 6 in that activity 9.
Okay.
And it turns out the key to answering, I think 7 was the one you were stuck on,
Right.
is having a clear answer for number 6.
Okay.
So do we think we can tell by looking at a denominator how long it's going to take to repeat or to terminate?
Tell by looking at the factors.
So what are the factors? So what's the key in the factors that tells us when it's going to terminate?
The highest power is how many digits it will have after the decimal point.
Yeah, and it's going to be the highest power of the 2 or the 5. The bottom line is if you have anything but a 2 or a 5 in a reduced fraction, it's going to go on forever. Question is, why do 2 and 5s behave nice and everything else not behave?
2s are evens and 5s want to go 5, 0, 5, 0. We're in a base 10 society.
Yeah, we're in a base 10 number system. Yeah, 2 times 5 is 10. That's why. If you divide by anything but 2, 5, or 10, you're going to have a non-repeating or non-terminating decimal. Okay? You're going to have a remainder all the time. Forever and ever and ever. It's the same set of remainders in the same order. Okay. So in order for a fraction to have a terminating decimal, its factors have to be only 2s and 5s in the denominator. The highest power of the 2 or 5 tells us how many places we have to go. Question, why?
Why?
Christian, why? You have an idea? Why does the highest power of 2 or 5 tell us when it has to terminate? Okay, here's a cube. Ready? Check this out. Somebody please read this number to me.
5 100ths.
Okay, 0.05 is slang, 5 100ths is the correct way to read it. That is 5 100ths as a fraction. If I wanted to convert this fraction to that fraction, what should I multiply top and bottom by? Multiply top and bottom by 5. Now, what happens when you do that, so I'm just going to rewrite that in a new screen. 1/20th is the same as 1 over 5 times 2 squared. Agreed? If I want to turn this into a decimal fraction, well, I would multiply the top by 5 and the bottom by 5. Because what that gives me is 5 squared times 2 squared. Or if I rearrange those, the denominator is now 5 times 2 times 5 times 2. Why is that important, rearranging them that way?
It's 10 times 10.
Yeah, because that's 10 times 10. I just made a decimal fraction. Decimal fraction means the denominator has to be a power of 10. 5 times 2 squared is not a power of 10. To be a power of 10, the 2 and the 5 have to have exactly the same power. Powers of 10 are things like 10 squared. So if I have a 2 squared, I need a what squared here? A 5 squared. So let's try again. Let's play the same trick on 140. 1 over 40, and then we're going to factor 40. Let's see, 2 goes into 40, what, 20 times? 2 goes into 20, 10 times. 2 goes into 10, 5 times. So 1 over 40 is 2 cubed, 2 cubed times 5. That's not yet a power of 10. How many 5s do I need to multiply by to get a power of 10?
2.5.
How many 5s?
1.
I need 1 more 5. So now I have 5 squared. Two cubed times 5 squared, is that going to be a power of 10? Okay, what's 10 equal to? 2 times 5, right? So you need as many 2s as you have 5s. Do I have that yet?
We need 3.
Yeah. So I can put 1 5, but I have to put another 5, because for every 2 I have, I also need a 5. Okay, so this, I've just created right here the third power of 10. What's the third power of 10? 1,000. What do I have in the numerator? Oops. $25. So apparently, 1/40th is the same as 25 thousandths.
You're texting a calculator.
The decimal fractions are what we're playing. So we got to build the decimal fraction. Highest power was a 3, so that means there's going to be 1, 2, 3 decimals in the answer. Okay, just the way it works. So the harder, so this was question 6 in activity 9. If you haven't gotten there yet, you better get there quick. Question 7 asked a much tougher question. Question 7 said,
Wait, what question was that previous one?
that was number 6
Number 6.
in activity 9. Okay. What, let's see if I can phrase this correctly.
Do you want me to read it? It's right here.
I'm going to rephrase it my way.
Okay.
Sorry. What about, what about the denominator? Tells you when a repeating decimal will start to repeat.
What would be the opposite rule of?
I think that's the essence of it. So I better look since really has it right there, which is Danielle. For fractions and lowest terms, okay, I skipped that part. Repeating decimals. How can you predict the number of digits between the decimal point and the repeating block? Yes, that's basically what I said. Slightly different way. All right, so whip out your calculators, help me out here. Or you might remember this from the other day. What's 1/9 as a decimal?
1.
Yeah, it's a whole bunch of ones. I happen to be familiar with 1/7, so I should do dot, dot, dot. 1/7 is 0.142857. 0.42857. Dot, dot, keeps going. Both of these start repeating immediately. Let's see. How about one we looked at the other day was 79. No,
It was
71. Okay, I'll make it up. So what I did is I think I took 1/10 and
it was
added it
79
to
over 890.
79 over 90. Yeah, so I took 1/10 and added it to 7/9, which gives us 79 over 90, which is 0.8777. So finally I have a fraction that as a decimal doesn't start the repetition till the second place. And let's see, I got another sneaky one I forgot to write down. Let's take try 13/36. That should be equal to 0.36111111.
Yes.
3 and the 6 never repeat, only the 1 repeats. So what we want to do is, like we had a rule earlier that said when we're terminating decimal, we'll stop terminating, we'll terminate. When will a repeating decimal finally start to repeat? Can the denominator tell us about that? So here we can see starts immediately, waits 1 place, waits 2 places. So what's different about this denominator and this denominator compared to this denominator and that denominator? That it delays the repetition.
Well, we have singles versus double digits.
So okay, single versus double digit. Here's another example. What if I had 13 over 99? What's that going to be?
1313 repeating.
Okay, so this starts repeating immediately, and I still have a double digit denominator. Okay, so it's not the double digits there. In the previous question, what did we have to do to answer the question? We had to factor the denominator. Yeah, so let's look at some denominators factored. So new page, 9 factors as 3 squared. 7 factors as 7 to the first. Both of those started repeating immediately. Right? 99, that's what, 9, which is 3 squared, times 11. That started immediately.
So that would be the prime factorization of the denominator.
The prime factorization of the denominator.
Okay, I was
That's
wondering what
yeah, that's part of the earlier part of the project.
Yeah.
So you've done, if you did the project, you would have already done a bunch of this.
Yeah, this is, I had a question about that.
Okay. So some of the other numbers I listed were like 90. Let's see, 90 is what? 9 times 10? And 10 is 2 times 5. So 90 is going to factor as 2 times 3 squared times 5, if I put them in order. What was the other one? 36? 36 is what? 4 times 9? So that's 2 squared times 3 squared. So here's a hint. What base number system do we have? Yeah, so this, the hint here is base 10 is the key. So what are the factors in the ones that repeat immediately? 3, 7. Okay. What are the factors of the stuff that delays a little while? What's there that's not in the other ones? 2s and 5s. Yeah. The 2s and the 5s make a difference. Why do 2s and 5s make a difference?
Because they can only go into things that end in 0.
Yeah, together they go into things that, well, together, I mean, they make a 10, and so that gives us a delay. So if I have a 2 squared here, and I want to turn 2 squared into a power of 10, what other number needs to go into the bottom?
2. Oh, 5.
A 5. I need a 5 squared. Right? If I take 2 squared and 5 squared and I put them together, what number do I get? 10 squared, which is 100. If I take a 2 and a 5 and put them together, what do I get?
10.
10. Okay. So when I divided by 90, when 90 was my denominator, how long did it take to repeat? 1 place. When I had a 2 and a 5, or sorry, a 2, what was it, 2 squared? Yeah, 2 squared as a factor in the denominator, how long did it take to repeat?
2.
You start to see a pattern now? Okay. So I'm going to give you another fraction, and without plugging it into the calculator, I want you to guess how long it's going to take to repeat. Give me 1 sec to make a fraction. How about, oh, that's a good one. Nice and simple. So no calculators yet. I want you to guess how long it's going to take 5, 6 to repeat. First, do we believe it will repeat or terminate? First, we should determine that. Or 5, 6, terminate or repeat? Why do you think it'll repeat?
That's 3.
Yeah, because 6 is 2 times 3. This is 5 over 2 times 3. And the 3 is going to make it repeat. Okay. What's the 2 going to force to happen?
Slow down.
Slow it down.
It's gonna make it wait 1 place before it repeats. That's what should happen. So looking at this, the 3 tells me it's going to repeat. The 2 says it's going to wait 1 place before it starts repeating. Now type it into your calculator and see what happens.
833.833.
Yeah, and it's not till the 3 it starts to repeat, right? So we can predict that by looking at the factors. And that's what question 7 was getting at. That's a tough question.
So the exponent tells you how many places it's going to wait, you said? If the 2 had, say, if the 2
power,
had
the highest power of a 2 or a 5.
Okay.
So if I had something like 13 over 2 squared times 5 times 3, let's say that was my denominator. Looking at this, I'd be able to say the 3 says this is going to have to repeat. And the highest power of the 2 or the 5 tells me that it's going to wait
So that's what 2 places.
2 places
Okay.
before it starts to repeat. So I'll type that into Google and see what happens. So let's see, that would be 10 times 6. So that would be 13 over 60.
Can you do this one?
Hang on one second. We'll calculate it out. So I think that's 13 over 60, if I did my math right, which would be 0.2166666. So it does repeat, it waits 2 places to do so. Okay. Which one, Elliot?
4,179.
4,179. Oh, where are they doing that? Whoa, what happened?
Your thing left, Jeff.
Okay. I think I just hit the funny button again. Ooh. I did something bad. Oh, there it is. It's just slow. Erase. Okay, let's try that one more time. 4,000.
179
Yeah.
over 4,950.
All right. So what do we want to do with this?
Find the decimal.
Find the decimal. Do we have to do anything else?
Yeah, the
The
prime.
decimal is easy. We just plug that in the calculator.
The prime factorization and
Of the denominator.
yeah.
Okay. So we got to factor that. So big factor tree.
Well, we know 50 will go into it.
Yeah.
Yeah, 50 will go into it, won't it?
But
is
you
that
have
true?
a 3, 5, and a 2 in it.
Yes.
Yes.
The denominator?
50 will.
Actually,
99 times.
50 goes at 99 times. Okay.
It ends in a 50.
All right. So 99 times 50.
Yeah.
What were you going to say, Christian?
What I basically saw first off is that if we look at the, what I basically got was 4,500 plus 450, which were both multiples of 9 and 5, or multiples of 9 and 5. So, sorry, I'm confused as I'm trying to say it. So basically 45 to the 45 to the 100th place and 45 to the 10th place. That's what I saw.
We see multiple 45s in there?
Yes.
Okay. So I'm going to go with this one how to factor it. So this is going to be what? 9 times 11. And 9 is 3 times 3.
2 times
50.
3 times 3 times 5 times 5 times 11.
Way ahead. 25. 5 times 5. Okay, so we have a denominator
11.
of 2 times 3 squared times 5 times 11.
Yeah, well, I was just wondering because
5 squared.
5 squared. Thank you.
you had said something before about the 2, if the 2, the 5, and the 3
Yeah.
were all in it.
So the 3 and, so now provided, is this a reduced fraction? So then I have to double check to see if anything comes out of that. Now, I don't feel like factoring that right now. Does anybody mind if I don't? Yeah, there's tons of factoring programs online. So I can just come here and type factor. Okay, that's at 4179.
3 times 7 times 199.
Okay, you got it already. Let's see, where's that? Where's back to pairs? 3 times 7 times what?
199.
199. 3 times 7 times 199. So one thing I notice is one of the 3's factors out, but that's not significant. If the 3's and the 11 disappear, this would have to terminate. Right? But since there's a 3 and 11 left behind, those guys tell me this thing repeats.
Okay.
So
The 2 and the 5 squared tells me what?
After
That's a delayed repeat.
How long does it delay?
2.
Delay is 2. The highest power of the 2 and 5 tell me that.
So the 2 or the 5 or the 2?
The highest power of either the 2 or the 5.
And it's same with the repeating, it could be the 3 or the 11.
Well, both the 3 and the 11 contribute to its repeating pattern.
But if it just has a 3, it'll repeat. If it just has 11, it'll repeat.
Correct. If it has anything but 2's and 5's in the denominator that don't reduce out, it will repeat.
Okay, that's what I was wondering.
Anything but a 2 and a 5. If the denominator is only made of 2's and 5's, it has to terminate. Why? Because it's a base 10 number system. It's just the way it
The 2 and 5 terminate everything else.
Okay.
So those guys delay 2 places for the repeat.
So is that after the, say, point whatever, and then 2 places? Or
Decimal point, 2 places, then it starts to repeat.
Well, I got it repeats after 3 places.
Okay, let's double check. So Google Calculator. So we have, what was it, 4179?
Yeah, divided by
Divided by
4950.
4950. So
Yeah, that's right.
0.84, and then it goes 4,
Oh,
2,
is it 4,
4,
2?
2, 4, 2, 4. So,
Because I started at the 242424.
that's true. There are different ways you can write it, but you can use one with less ink. Right, so 84424. Yeah, so I see what you're saying. So let's write this down. So new page. So this is 4179 over 4950, and it's equal to 0.844242, and then it just keeps going like that. And so I could write it like this: 0.844, and say the 2 4 repeats.
Yeah, that's what I did.
Or I could say it's 0.84 and then the 4 2 repeats.
Okay,
And this would be the more common way to write it because it uses less ink.
okay.
Yeah.
That makes sense.
There's always a simplest way to write the repeating part, but there's always different ways to put the bar on top. One always uses less ink. So both of those will lead to the same exact decimal. And this one version here matches our analysis of this denominator.
So I changed my answer to number 7. Do you want me to resend that to you or no?
Just resend your answer to 7. Unless
Okay.
did you just erase what you had and rewrite it?
Yeah.
Okay, you can just send me the whole thing, that's fine, the whole page,
Okay.
that's fine. Okay, so check this out, this is kind of interesting. I mentioned this in class the other day, that if I take a right triangle that measures 1 unit that way and 1 unit that way, and I connect those endpoints together, this side right here is the longest side, is called the hypotenuse. Hypotenuse. Is that the right time? Right time is on. All right, I'll finish this quick. What theorem that's famous can I use here?
Pythagorean.
Pythagorean theorem. So, theorem. It says if you take the legs are usually called A and B, and you square them and then add them up, that's always going to be equal to the square of the long side. And C over here is what we call the long side. These guys are called the legs. So following that theorem, if we believe it to be true, we would get 1 squared plus 1 squared, well, that's just 1 plus 1, is 2. So that tells me I'm looking for a number whose square is 2. Well, that'd be 1 plus 1. 1 times 1 is still 1, right? So that doesn't work. So we're going to try and find that number. And we're going to do it by experimenting. So what about a calculator? We want to figure out what number squared is 2. Now 1 squared is 1, so that doesn't work. And 2 squared is 4, so it's got to be somewhere in between. So I'm going to whip out a spreadsheet here to help me with this. You can whip out your calculator. So we might guess, if it's not 1, if it's not 2, it might be 1.5.
Too much.
1.5 squared, I think, is what, 2.25? Now, we could spend a while guessing, but we can apply a bit of trial and error to the system. We'll get to square root in a minute. That's the quick way.
It's like 4.1, 3.415.
Number square. Oops, that's one more, right? 1.5, 1.4. And the square, I just say equals click square, and then I can just fill that down and start typing stuff. So 1.4 is too low, so I go 1.41. Still too low. 1.415. Too high. 1.414. Too low. let's see. 41. Oops, I didn't mean to type over that. 414. 1 point. It's got to be bigger than 1.414, right? It can't be 1.415.
4, 1.
So I could go 4141. Too low. 1.4142. Oh, getting there. 1.4143. Ooh, too high. So what I'm doing is I'm nailing digits one at a time, right? I now know it's about 1.4142. That's not bad. That was pretty fast.
13562.
Okay, so then, yeah, we could just say, hey, what's the square root of 2? So over here on a computer, SQRT is the standard abbreviation for square root. So I type that equals SQRT, and then I type a 2. And now I have a number whose square root is exactly 2. You know how I use the Google calculator here a lot? So here, if I type SQRT, oh gosh, whoa. Maybe up here, if I type SQRT and then give it a number, it automatically believes it to be the square root of 2, and I type the whole square root right there. Now they have a little shorthand button for it here. Problem with the square root of 2. It can't be written as a fraction. So we have a trick in math called that little symbol right there, the square root. And that's the exact answer. Now, if this was a fraction, then we would be able to say some whole number a divided by some whole number b has to be equal to the square root of 2. Alternatively, if we square a over b, then that would have to be equal to 2. But it turns out there's a problem if you try to make that true. And if you read section 8.1, which I would like you to read this weekend, I think on the 3rd page of 8.1, they try to explain the problem with that. This ends up being false. Can't happen, impossible. And one of the Pythagoreans a few thousand years ago realized this, and I think he was skinned, and then they cut his arms and legs off, and I think they threw him in the ocean to be eaten. Crazy stuff. One more thing and then I'll shut up.
So they didn't like this.
What's that?
So they didn't like.
Yeah. Check out this number right here. 1, 0, 1, 0, 0, 1. What should I write next?
0, 0, 0.
0, 0, 0, 1. So you guys can continue this pattern, right? Okay. So dot, 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 continue. There are numbers like the square root of 2 which can't be fractions. Then there are numbers like 1/3 and 1/2 that clearly are fractions. Is this number a fraction or not? So, your homework this weekend, read 8.1. I have a couple more things to say about 8.1 on Monday. That'll only take half the time, and then we're going to start reviewing for a test. God. We're not going to cover the rest of Chapter 8. We're going to skip to Chapter 9. In our course website, I posted a couple of practice exams. I wrote a take-home exam. I can post it now or Monday.
No.
Post it now.
Okay. We can start doing it. I can post it now.
Do Wednesday.
And it'll be due, yeah, Wednesday, a week from today. So let's see, is that in here?
Do the 17th.
How did you write the practice exam before or after you had some?
This was after I slept for 12 hours, yes. So I felt pretty good writing this one. It's going to come up right here. So like the previous exam, I just wanted to show me you can do some decimal arithmetic without a calculator. Now this is super important. You're at home, I can't really see you not use a calculator, so I would check with a calculator. Now you're gonna have to do the same thing on the in-class test, and then it would be illegal to use a calculator. But just, you know,
Just so you know what to do,
100% on part 1, don't miss anything there. And then we got some things that we went over in class. So show me some things about a number with base 10 blocks. Like how could you use base 10 blocks to show somebody 2 3500s? Find some numbers between 3.14 and 3.15.
3.141.
Yeah, so that's not going to be too bad. Can you put these numbers in order on a number line?
Oh.
That's a little trickier. Can you turn these repeating decimals into fractions? We practiced that a couple of times. That's kind of tricky sometimes. Stuff we talked about today. How can you determine if a fraction will terminate as a decimal by looking at the denominator?
So number 5 we're supposed to be able to do without a calculator?
I don't say that. Only number 1 I said don't use a calculator. Yeah, the rest of it I don't say don't use a calculator. You could do number 5 without a calculator.
Yeah, 3.0.
But I would like a calculator for that one. Show me pictures of 2.3 times 1.4, like what was that, activity 6?
Yeah.
And then we talked about how to use base 10 blocks to do division. We can practice these on Monday. Percent off we went over on Monday. Investments we went over Monday and today. And then this is a question from 8.1, which I haven't talked about, but you're going to read about, and we will talk about on Monday. Okay. So this is the take-home test. I'll post this. I have it in my Google Docs. I'll put it in hang on, Debbie, what was it?
I watched the, because the link didn't work for Monday, and I watched the video that you posted, but there was no examples of dividing. Could you maybe send me something like that?
Like examples for number 9?
Yeah.
Okay, yes, let me make a note of that. I did that last week.
Oh, that wasn't from Monday?
No, that wasn't from Monday.
Okay, then I probably have it in my notes.
Yeah, on Monday,
Cut
what did I
class
do?
short.
Not much though, we went to like 1 or whatever, 20. We cut class 20 minutes short because I wasn't feeling well.
Oh.
On
So
Monday,
it was percentages.
we went over percentages, we went over changing fractions to decimals and decimals to fractions. Oh, and we went over another multiplication problem. Like the array that I sent you.
Yes.
Yeah, so we went over the multiplication arrays, we went over fractions and decimal conversions, and we went over percentages.
Okay.
And everything but the reviewing fractions and decimals and the reviewing the multiplication arrays was in that video I sent you.
Okay.
So if you don't find something on division in your notes, let me know and I'll get something out there.
Okay.
And we can definitely review that on Monday. Hillary, I have a question.
Yeah.
On the activity? Okay, I'll come help you with that. All right, so that's it for today. Have fun. Thanks for staying late. My apologies for keeping you late. I'll see you soon.
Thank you.
Yeah, bye-bye.